In the first part of the Fundamental Theorem of Calculus, we were given a way to evaluate a definite integral. The second part of the Fundamental Theorem of Calculus is what ties differential calculus and integral calculus together. Now, before we move on, one thing to note is in your notes, it says df dt, so go ahead and make that change. It should be df dx here, so make sure that you make a note of that. So it says if f is a continuous function on the closed interval from a to b, then the function big F of x is equal to the integral from a to x of f of t dt, has a derivative at every point x in the closed interval. So notice in this that the function here is in terms of t, and then we have a, which is a constant in our lower limit of integration, and our variable x, which is a function of x in our upper limit. So basically what the second fundamental theorem of calculus says is if this is true, if f of x is equal to the integral from a to x of f of t dt, and I want to find the derivative, then the derivative of our function, capital F, is equal to the derivative of this integral from a to x of f of t dt, right? It's just equal to f of x. So what this is basically saying, so in a nutshell, what this says is if you take the derivative of an integral, you get your integrand in terms of the variable that you're integrating with respect to, or in terms of the variable you're taking the derivative with respect to, sorry. So you would get that there. Now, this has to have a constant of integration in our lower limit, and then our variable in our upper limit of integration for this to work. So basically what's happening is you're just taking this variable here and you're substituting it into your function when you're taking the derivative. So let's go ahead and see how this works, and then I'll kind of show you why this works in an example. Okay, so we want to apply the fundamental theorem of calculus here. So we are told that we want to find the derivative with respect to x of the integral from pi to x of sine of t dt. So the fundamental theorem of calculus says that this should just equal, since we have a constant lower limit of integration and we have an upper limit of a variable x that we're taking the derivative with respect to, I should just be able to substitute x into my argument for the sine. And so this should just be equal to the sine of x. Okay, so let's talk about why this works. So this is the correct answer, but why? So let's go through the process of actually doing the integral here. So if I integrate this and then I take the derivative, what would I get? So if I want to take the derivative with respect to x of, so if we integrate, so what function has an what function has a derivative of sine? The antiderivative of sine is the opposite of cosine, and we're doing this with respect to t. So we're going to go from pi to x here. So let's go ahead and evaluate the antiderivative, and then we'll take the derivative of it after that. So the derivative with respect to x of, so plugging in the upper limit of integration, so it's negative cosine of x minus the opposite of the cosine of lower limit of integration is pi. So what do we get here? So we have the derivative with respect to x of negative cosine of x. Cosine at pi is -1. So subtracting -1, that becomes positive. So it's negative cosine of x minus 1. Okay, so now take the derivative of this. So the derivative of cosine is opposite of sine, but we already have a negative there, so we end up with positive sine of x. And then the derivative of a constant is 0. So I just get sine of x. And we saw that right in here. All we had to do was take our upper limit of integration, which is our variable, and substitute it into the argument for our function there. And that's basically what the fundamental theorem of calculus tells us we can do. Now, this only works when we're taking the derivative of an integral, right? So it's kind of what ties together these two pieces, right? The second part of the fundamental theorem of calculus essentially is showing us that the derivative and the integral are inverse relationships of each other, right? They're inverse processes. Okay. Now, what if we have an upper limit of integration that is not just an x, right? In this case, we have an x squared. So what would I do here? So basically, in this situation, you would take your x squared, you would plug it into your function there, but then you would also have to multiply by the derivative of the inside. Because again, remember, we're really actually taking a derivative here. So when we are taking the derivative and we have it on the inside, we keep the function on the outside the same, leaving the or we take the derivative of the outside, leaving the inside alone, and then have to multiply by the derivative of the inside. So we ultimately will have to multiply by the derivative of this x squared here. So what will that look like? So if y is equal to this, then dy dx is equal to the derivative with respect to x of the integral from 1 to x squared of the sine of t dt. So if I substitute in, this is going to be equal to, so I'm taking the derivative of this, so it's going to end up being the sine of x squared, and then times the derivative of the inside of this. So let's go through. I want to show this one again using the actual process of doing the antiderivative and then differentiating. And then I won't for the rest of the ones in the future. Okay, so take the antiderivative of this, and I'm going to get this is the opposite of cosine of t evaluated from 1 to x squared. So if I actually evaluate this, I get that this is equal to the opposite of the cosine of x squared minus a negative cosine, so it's going to be plus cosine of 1. And I want to take the derivative of this. This is what y is equal to. So I want to take the derivative of that. So then dy dx is going to equal the derivative with respect to x of negative cosine of x squared plus cosine of 1. Now, cosine of 1, this right here is really just a constant. So when I take its derivative, it's going to be 0. So derivative of this, so it's derivative of the outside. So derivative of cosine is the opposite of sine, which is going to make this positive sine, leaving the inside alone, times the derivative of the inside by the chain rule, and then it's going to be plus 0. So we end up with exactly what we saw we had there in the first place. Okay. So for this problem, what do? So in this case, remember we said in order for us to be able to use the fundamental theorem of calculus, we need to have a constant in our lower limit and our variable in our upper limit. So I know that through properties of limits, I can switch my limits of integration if I just take the opposite sign. So this is going from 5 to x of sine of t dt. So now I can just apply the fundamental theorem of calculus and say, okay, well, if that's the case, then dy dx is going to equal the derivative of this, right? The opposite of the integral from 5 to x of sine of t dt. And so basically I can take this x here, substitute it in for t. Since it's just x, I don't have to do the chain rule. And I'm going to get this negative that's going to multiply that. So it's going to be negative sine of x here. All right, so what do we do in a situation like this? So now we have variables in both our upper and lower limit. Variables in both our upper and lower limit. So if you guys remember, right, if you remember, there's a property that said if I have the limit from a to b of f of x with respect to x plus the integral from b to c of f of x with respect to x, that's equal to the integral from a to c times f of x with respect to x, of f of x with respect to x. Okay, so you notice here, right, we have the upper limit of this one is equal to the lower limit of this one. And so it kind of creates this like string of integrals where they're broken up at b. And we can combine that and say, okay, well, then that's just equal to the integral from a to c of this function here. So we actually want to do something like that with this here. And we're going to make it so that we're going to cut this, we're going to split this at some constant value and then rewrite it as an integral where we have a constant as a sum of two integrals where we have constants in what are lower limits. Okay, so let's go ahead and do this. Let me move this up here, and then let's go through and do this here. So I'm going to say that this is going to be equal to, I'm going to use it 0. So I'm going to have this go from 2x to 0 and then from 0 to x squared. So it's going to be equal to the integral from 2x to 0 of our function, 1 over 2 plus e to the t dt, plus the integral from 0 to x squared of 1 over 2 plus e to the t dt. Now I know that in order for this to work, I have to have my variable in my upper limit. So that's going to be equal to, so the y is going to equal the opposite of this from 0 to 2x of 1 over 2 plus e to the t dt, plus the integral from 0 to x squared of 1 over 2 plus e to the t dt. Okay, so now I can substitute, right? So anywhere I have, oh, this is a terrible t right there. That should be a t. Anywhere I have a t, I want to substitute in my variable, and then so I'm taking the derivative of this, right? So dy dx equals, so I'm going to take this, substitute it in for t, and then because it's not just an x, I have to multiply by its derivative through the chain rule. So it's going to be negative 1 over 2 plus e to the 2x times 2. So I'm just going to make this a 2 in the numerator, right? Because it's 1 times 2 there. And then plus, and I'm taking the derivative of this. So I'm going to take the x squared and plug it in. So it's 1 over 2 plus e to the x squared times its derivative, which is 2x. And again, because I'm just multiplying by 2x, I'm going to put it there in the numerator. So this is our derivative using the fundamental theorem of calculus, right? It's our derivative of this integral here. So another thing that we get out of the fundamental theorem of calculus is something called the net change theorem. And what the net change theorem does is it tells us the amount of change, the total change, or the net change of our function on some interval from a to b. So if I want to know the net change of capital F, well, that's going to be found by taking the integral from a to b of its derivative with respect to x. So if I integrate the derivative of my function, so basically f prime is our rate of change, it's our derivative of our function f. If I integrate it on the interval from a to b, I get the net change of my original function. And this is actually very useful when we're dealing with position, velocity, acceleration problems, because this net change, if we look at the net change in the velocity, that's actually just the change in, or sorry, if we look at the integral of the velocity, that's just the net change in our position or our displacement. And we can basically, because remember the derivative of position is velocity, so take the antiderivative of velocity. I'm going to get the position at time b minus the position at time a. And this basically just tells me how much my position has changed on that interval. And then you could also do something similar, find the net change of velocity using the acceleration function and so on. Now, one thing that's pretty nice is if I'm looking for like my final position, right? This is my final position here, and then this is my initial position here. To find my final position, I can just add my initial position, right? So the final position is equal to your initial position, right? So basically we have, let's just write it like this. The final position, S of B, would just be equal to the initial position, S of A, plus the integral from A to B of our velocity function, which is just the displacement, right? So we are looking at, if we want to find the final position, you just take your initial position plus your displacement. It would help to write the full word, right? Plus your displacement to find its final position. Okay, so in this example, we are given the velocity function in meters per second of a particle moving along the x-axis for time between 0 and 9 seconds. We want to use analytic methods to evaluate the following things. So A, we want to determine when the particle is moving right, left, and is stopped. We want to find the particle's displacement. So that's just that integral we were looking at. This is saying if s of 0 is 3, so that's the initial value there, what is the particle's final position? And then what's the total distance traveled? So we'll talk about those things here in just a second. So first, how do we know when a particle is moving right, left, or stopped? So a particle moves to the right when the velocity function is positive. Oops, sorry about that. It moves left when the velocity function is negative, and it is stopped when the velocity function is 0. So the first thing that we want to do is figure out when is the velocity 0. Because in order for the function to change direction, it has to first cross through the x-axis. So this happens when, so we have 10 minus 2t equals 0. So that's going to be when t is equal to 5. So we can go ahead and do a sine analysis here. So remember, we're going from 0 to 9. So 5 and then 9. And this is the velocity. So if I pick a number between 0 and 5 and plug it in, what do I get? So let's say like 4. 10 minus 8, that's going to be positive. Pick a number between 5 and 9. Let's say 6. 10 minus 12, that's going to be negative. Okay. So this tells me then that my particle moves right. So it moves right for t between 0 and 5 seconds. It moves left for t between 5 and 9 seconds. And it's stopped at t equals 5 seconds. Okay, so this is part A. Part B is asking us to find the particle's displacement. So remember, the displacement is s of b minus s of a, which is found by taking the integral of our velocity function from a to b. Okay, so we can do that. So what is so it's going from 0 to 9, so it's from 0 to 9. The velocity is 10 minus 2t dt. Okay, so I don't need this. Let's just move this over here. Okay. So antiderivative of 10 is going to be 10t. Antiderivative of 2t, that's going to be 2t squared over 2, which is just going to be t squared. And we want to evaluate this from 0 to 9. 0 to 9. And this is giving us the displacement. So always plugging in the upper limit first. 10 times 9, that's 90. Minus 9 squared is 81. Minus, plugging in our lower limit, that's going to be 0 minus 0. So we get 90 minus 81, which is 9 meters. So in the first 9 seconds, it's only 9 meters away from where it started, because it was going right and then it turned around and came back left. All right, so let's go ahead and get a fresh copy of this here and go through the next part. So part C is asking us, what is the particle's final position? So remember, final position is, so that's when S of B, this is part C, was equal to S of A plus the integral from A to B of V of t dt. It's just your initial position plus your displacement. So let's go ahead and find that. So we want to know what is S of 9 if S of 0, right? So it's going to be equal to S of 0 from 0 to 9 of V of t dt. So we're told that the initial position is 3. And we just found this. This was our displacement. So we found that in the other part, in part B. That was 9. So the final position is 12 meters. So 12 meters away after 9 seconds. And part D. So the last piece here is talking about total distance. So if our particle is moving like this, right? If our particle is moving like this, the distance that it moved from where it started here, that's our displacement. It's not that far away from where we started, but notice it moved a lot further than all of that, right? So we can find our total distance. The way that you find total distance is by looking at the integral from, so this is total distance is equal to the integral from a to b of the absolute value of your velocity function. Okay? Now, if the velocity is negative, then we have to adjust the integral so that we always are making our velocity positive, right? That's what the absolute value is going to have to make us do. So we're going to have to adjust our limits of integration anytime that the velocity is negative. We're going to have to take the opposite of that value over that range. Okay? And we saw that the velocity was negative on the integral from 5 to 9, right? The interval from 5 to 9. So that's what we're going to have to do here. So this is going to be equal to the integral from 0 to 5. So on the first interval, the velocity was positive. So we can just use our normal velocity function. So it's going to be 10 minus 2t dt. On the interval from 5 to 9, it was negative. So we have to take the opposite of it. So 10 minus 2t dt. Okay, so let's go ahead and do the antiderivative here. So that's going to be, so we can pull this negative out also. So this is going to be 10t minus t squared evaluated from 0 to 5. And if I pull the negative out, it's just going to be subtracting this. And then that would be basically the same as this. So it's going to be 10t minus t squared evaluated from 5 to 9. Okay. So what are these values here? So if I plug in 5, that's going to be 50 minus 25. So that's going to be 25 and then minus 0. So this is 25 minus, plugging in 9, 90 minus 81. So that's going to be 9 there. And then plugging in 5, I already saw that's going to be minus 25. So 9 minus 25, that's negative 16, but we're subtracting it, so it's going to add. So 25 plus 16 is going to be 41. So the total distance traveled is 41 meters. Sorry, this is pretty terrible here. Let's write 41 meters. All right. So in this last example, we are given a graph of the velocity function at time t in minutes. And we're told that the initial position is 5 meters. So x of 0 is equal to 5. We want to know what is the position of the particle at the end of the trip. This is just the final position. And then what is the total distance traveled? So remember, for the final position, so first of all, it's going from 0 to 55 minutes. So we want to know what is the position at time 55. And that's going to be equal to our position at time 0 plus the displacement. So from 0 to 55 of our velocity function with respect to t. So this right here is really just the area under the curve. So I know my initial position. My initial position is 5. So this is going to be equal to 5 plus the area under the curve. So basically, we're going to have to look at the area here. Now, when I say under the curve, right, I mean between the x-axis and our curve here. So we're going to have to look at that area there. And then we're going to have to look at this area here. So the first area, I'll call this area 1. Area 1 is a positive area. And then area 2 is a negative area because it's below the x-axis. So I'm going to have to add area 1 and add area 2, but really I'm going to be subtracting area 2. Okay, so what is the area for area 1? So this is just a trapezoid. So we know the area of a trapezoid is 1/2 the base, or sorry, 1/2 the height. So the height here is 20, 40, 60 times the sum of the bases. So the top base is 5, and the bottom base here is 5, 10, 15, 20, 25, 30. Okay, so that's area 1. And then I actually have to subtract, right? I have to subtract this area because it's negative. And this is just a triangle, so it's 1/2 the base. So the a base is 5, 10, 15, 20, 25 times the height, which is 20, 40. Okay. So what do we get here? So this is 5 plus, this is going to be 35. So half of 60, that's 30. 30 times 35, what is that? That's 1,050. 1,050. And then half of 40 is 20. So 20 and 25, that's 500. So then it's going to be minus 500. So we get that the final position, so after 55 minutes, it is at a position of, so that's 1,055 minus 500, which is 555. What's our unit? Meters. All right, and then the last part is the total distance traveled. So remember, the total distance traveled for part B is the integral from 0 to 55, 55 of the absolute value of v of t dt. So in this case, it's going to be the integral from 0 to 30 of our velocity function, and then plus the integral from 30 to 55, but for the opposite of our velocity function, because it's negative and we want it to be positive. So we know that this integral here is the value that we had here, 1,050. So 1,050. And then we're adding the opposite of this. And the area here was negative 500. So we're going to be, instead of subtracting 500, we're going to be adding 500 here. So the total distance traveled is going to be 1,550. Now, we don't include this initial position here because this is where we're starting. We're not moving this 5 units, right? Or 5 meters, right? We're starting at a position of 5 meters, but we're moving this much. And that's why our final position does use it, but our total distance does not.